Thank you very much for listening to this recorded presentation. My name is Juan Garcia Bonilla. I'm a robotic technologist at JPL and a PhD student at CU Boulder. And I'm working with Hans-Peter Schaub at the ABS Lab to develop simulation tools. And today, in fact, I'm going to talk about a simulation tool for generally articulated spacecraft for GN&C algorithm design and validation. And so let's start with what we mean when we say generally articulated spacecraft. Well, as GN&C engineers, we like to think that our spacecraft are point masses or rigid bodies, but the reality is that they are usually more complicated than that. They have solar panels that deploy, they have reaction wheels that rotate, and even in bigger examples, we have space stations with like multiple components who move with respect to each other. We have robotic arms now in space. So generally articulated spacecraft are basically composed of multiple bodies, usually rigid bodies that move with respect to each other through joints or hinges. And robotics are called multi-body dynamic systems. And we're talking about this because, as I mentioned, we usually like to think that our spacecraft are point masses or rigid bodies. And that's very useful because the analytical equations of motion for these systems are very easy. I think everybody who's here in this presentation can derive them by hand. Now, when we start adding things like reaction wheels or perhaps solar panels, then you start having this coupled motion of like multiple masses moving with respect to each other. And although there is some solutions for these systems, like the pack substitution method, the reality is that these don't scale very well. And as the complexity evolves, and then you have like robotic arms, the model and simulation complexity, that is the equations of motion, how hard it is to derive them, how hard it is to treat this system, just grows exponentially, and even more when you consider flexible bodies, contact dynamics, variable topologies, etc. Now, our argument is that this exponential explosion of modeling complexity with the spacecraft complexity only happens when we're chasing analytical solutions. And our question is, okay, how can we empower GN&C engineers to explore this very interesting family of spacecraft, which are the future robotic arms, space stations, but without having to pay the price of modeling these complex equations of motion, deriving them by hand? And our solution to this problem are multi-body dynamics engines, which are things that are going to provide you a framework that is more abstracted, that's going to allow you to scale on complexity much more linearly. And even though you're going to pay some complexity up front when you're only considering point mass or rigid body spacecraft, as you start adding components, the complexity of simulation doesn't grow as it did before. And so I realized that not a lot of people who are listening to this presentation might know what a multi-body dynamics engine is, so I thought I would show a very cool video that is coming from the world of robotics. So this is a multi-body dynamics engine simulation that is called MuJoCo, and is used extensively in the world of robotics. And essentially it's something that allows you to model the kinematics and the dynamics of very complex articulated spacecraft or robots or anything that can be generalized as a generally articulated systems of bodies. Now, this is an incredibly powerful tool, and it's going to allow you to compute kinematics and dynamics in a very transparent way without having to worry about the equations of motion. And so our idea is to leverage these tools that already exist out there and save us all a lot of headache by splitting the work, where we have the GN&C engineer, us, on one side, and we have the multi-body dynamics engine on the other side. And the job of the GN&C engineer is really to define the spacecraft multibody, which is, as you're iterating through your spacecraft, you're adding a reaction wheel, you're adding a solar panel, you're making your hub heavier. This is like the definition of your spacecraft. And you're very importantly also defining the forces that act on the spacecraft, which is not only the environment model, so the gravity or the drag, but also basically all the GN&C loop, right? Because eventually all the GN&C is going to create some control force or torque on your system. Well, we leave the multi-body dynamics engine to do the kinematics. That is, it's going to analyze the state of the spacecraft, and it's going to output useful information to analysts like what is the pointing direction of a camera, or what is the position of a center of mass of the multibody or the spacecraft, or let's say what is the acceleration vector along this direction to model accelerometer. And very importantly, it's also going to compute the dynamics of this system. So it's going to take all the forces and torques acting on the system that you define through your GN&C and environmental models. It's going to compute, okay, what's my tan derivative of the states of the multibody. And so how we like to do this, how we like to split the work, is to use a message passing model-based approach. And what do I mean by that? Well, models are this self-contained calculation that is going to take some well-defined input, like the state of the spacecraft, and it's going to output well-defined outputs like the position of center of mass or the pointing vector of a sensor. And whatever is inside this kinematic model has to be, it can be transparent to whoever. It can be a black box to whoever is using this model. They only need to understand the input and output interfaces. This is a very useful pattern in simulation frameworks. You see it in math work. You see it in many other simulation tools like digital darts. And in this case, we're going to have two models, the kinematics and the dynamics model. The kinematics model is going to output things like the position and the rate, angular rate of your spacecraft. And the dynamics model is going to input forces, torques acting on the system. It's going to output the time derivative of your spacecraft, of the spacecraft states. And what goes inside, it's unknown to a GN&C engineer, and that's where we're going to leverage the multibody dynamics engine by inputting it inside these models. And the forces acting on the spacecraft, we're going to define through what we call the dynamic models, which are these pieces of user-defined mathematics or like GN&C algorithms that take well-defined inputs and outputs, and they're connected to each other to pass information around. And so effectively what we're going to get is the dynamic engine is going to compute position of the center of mass. It's going to pass it to a model, which is going to take it and then do some calculation, and eventually at the end of it, it's going to produce a force to be acted on the spacecraft. And then the dynamics model is going to take that and is going to produce the rate of change of the states of the spacecraft so that we can integrate the states in time. One example that I would like to show is this very cool solar panel deployment scenario where we have this branching configuration where we first deploy the main panels and then we're going to deploy a left and a right side. This exhibits very complex dynamics where all the masses are coupled and you have like conservation of momentum and things like this. But actually the implementation in a simulation framework like this is pretty simple. You define two models, one that gives you a desired position and one that gives you a desired velocity for the angles of all these panels in time. And you have the forward kinematics model, which is going to output the current angle and the current angular velocity of that joint. And you can compare the desired and the current angular velocity in a PID control model, for example, which is going to output a torque to exert on that hinge, on that joint, which is going to be fed into the forward dynamics model, and that is going to compute the rate of change of the entire spacecraft configuration. The video that you're seeing here, we produce with the software that we have at AVS. And it's a combination of Basilisk, which has a long heritage of good environmental models like gravity and aerodynamics, a bunch of GN&C algorithms, has sensors and actuator models, and it provides this message-based architecture that we're talking about. And the multibody dynamics engine that we're using is called Mujoko, which we previously introduced. And it gives you a lot of cool things like constraints and joint limits and contact dynamics and rendezvous modeling that perhaps implemented by hand in Basilisk will be unfeasible. And so I want to do a quick recap of what's extra on the paper. And we have three examples so that you can see the solar panel deployment that we very briefly covered and you can see in this video. And we're also going to have a very classical altitude control problem with reaction wheels to see how this paradigm applies to very classical altitude control systems. And then we're going to have a novel 6 degree of freedom control using thrusters that are mounted on robotic arms to see how this applies to more complicated, perhaps, like control algorithms are going to fly in the future. The paper contains a lot of code excerpts and actual multi-body definition files, so you can see what is the complexity of treating with a tool like this, and hopefully you come out of it thinking that the API is designed in a way that is very GN&C centric. It's designed in a way that is very easy to use for GN&C engineers. And also there is our public repo that has even more examples that you can always check out. And so very quickly to go over my conclusions, We argue that we can leverage multimodal dynamic engines to empower GN&C engineers to very quickly and agilely explore complex spacecraft configurations at a lower complexity. We also show that we integrated Basilisk with Mujoko, and we're exploiting the power of these open source robotic tools while maintaining a GN&C oriented simulation design that is provided by Basilisk. And finally, we also show 3 usage examples in the paper that range for very complex articulated spacecraft, like the solar panel deployment scenario, to more traditional or novel GN&C scenarios. I want to quickly acknowledge the JPL because they're sponsoring my PhD. And finally, if you have any questions, if you miss me at the conference, please shoot me an email. I'll be more than happy to field any questions. Thank you.